nuclear part, right? So in that we have discussed all these particle physics we have completed already. So one class or one or two class particle physics class record ಆಗಿಲ್ರಿ ಊರಿಗೆ ಹೋದಾಗ. ಸೊ ಅದನ್ನ ಬಿಟ್ಟರೆ ನ್ಯೂಕ್ಲಿಯರ್ ಪಾರ್ಟ್ ಈಸಿ ಅದ. ನ್ಯೂಕ್ಲಿಯರ್ ಪಾರ್ಟ್ ಬೇಸಿಕ್ಸ್ ಇಂದ ಕವರ್ ಮಾಡತ್ತೀನಿ ಈಗ. ನ್ಯೂಕ್ಲಿಯರ್ ಪಾರ್ಟ್ ಸ್ಟಾರ್ಟ್ ಮಾಡ್ತೀನಿ ರೀ ಈಗ. ಸೊ ಒಂದು ಅಥವಾ ಎರಡು ಕ್ಲಾಸ್ ಅದಲ್ಲ, ನಿಮಗೆ ಬೇಕಂದ್ರೆ ಮತ್ತೊಂದ್ಸತಿ ರಿವಿಷನ್ ಮಾಡ್ಕೊಡ್ತೀನಿ ರೀ. ನಾವು ಊರಲ್ಲಿ ಇದ್ದಾಗ ಟ್ಯಾಬಲ್ ತೊಗೊಂಡಾಗ ಅದು ರೆಕಾರ್ಡ್ ಆಗಿಲ್ಲ ಕ್ಲಾಸ್. ಅದನ್ನ ಬಿಟ್ಟರೆ ಈಗ ಪಾರ್ಟಿಕಲ್ ಫಿಸಿಕ್ಸ್ ಸ್ಟಾರ್ಟ್ ಮಾಡಿದ್ದೀನಿ ನಾನು. That I'm going to continue from now onwards. In the nuclear physics, I have covered some of the points regarding like basic nuclear properties. So just I will quickly I will revise all those properties, then I'll go to the next part. So, so is the screen is visible properly? Everyone? Yes. Okay. So nuclear physics. Okay.
Yes, sir.
So nuclear physics concept. So in this nuclear physics, I have already covered like topics of a basic nuclear properties. Like basic nuclear properties, even ನೀವು ಆಲ್ರೆಡಿ ಇದನ್ನ ಕಲ್ತಿರಿ ಕಾನ್ಸೆಪ್ಟ್, ನೀವು ಇವನ್ ಇದನ್ನ ನೋಡ್ಕೊಂಡ್ರು ನಡೀತದೆ. ಸೊ ಇದನ್ನ ಜಸ್ಟ್ ರಿವಿಷನ್ ಮಾಡ್ಕೋರು ಸಾಕು, ನಡೀತದೆ. ಸೊ ದಟ್ ಹ್ಯಾವ್ ಡಿಸ್ಕಸ್ಡ್ ಅಬೌಟ್ ಇನ್ ದ ನ್ಯೂಕ್ಲಿಯರ್ ಪಾರ್ಟ್, nuclear physics, like what are isotopes, so what is nucleus, what are isotopes, then so here I have discussed about isotopes, then isobaric isobars isobars, then isotones. Then we discussed about isomeric nuclei. Then we discussed about mirror nuclei. Okay, so mirror nuclei. Then we discussed about what is that is defined as so radius and density, mass density, radius part. So here see isotopes. What do you mean by isotopes here? How do you define these isotopes? Firstly, isotopes are nothing but see nucleus ಅನ್ನ define ಆಗಿ ಮಾಡ್ತೀವಿ. So if I define this X ಅನ್ನೋ nucleus ಇತ್ತಂದ್ರೆ it is atomic number and A is atomic mass number, isn't it? So one is mass number, another one is atomic number. Then here this part isotopes means, so especially isotopes means same ಇರ್ತದ್ರಿ. atomic number Z ಏನಿರ್ತದೆ, atomic number Z is going to be different. So Z different ಇದ್ದು atomic mass number same ಇತ್ತು ಅಂದ್ರೆ ಅದಕ್ಕೆ ಏನಂತ ಕರಿತೀವಿ ನಾವು isobars ಅಂತ ಏನು isotopes ಅಂತ ಕರಿತೀವಿ, isn't it? So isotopes same Z but different mass. So Z's will be same, masses will be different. So same Z with different mass. So Z will be same, but A mass will be different. Correct? So different. So this is the main thing. This is the difference that is defined with isotopes. Next is isobars. Isobars and re-entry. Isobars means here we are going to have same A but different Z. Isobars are same Z and different atomic masses. ಬೇರೆ ಬೇರೆ ಇತ್ತು ಅಂದ್ರೆ ಅದಕ್ಕೆ isobars ಅಂತ ಕರಿತೀವಿ. Similarly isotones, I told isotones means same number of neutrons, same number of neutrons. So same number of neutrons ಅಲ್ಲಿ ಇರೋದು ಅವೆಲ್ಲ ಏನಂತ ಡಿಫೈನ್ ಮಾಡ್ತೀವಿ ಅಲ್ಲಿ ನಾವು isotones ಅಂತ ಡಿಫೈನ್ ಮಾಡ್ತೀವಿ. Okay.
Sir,
Isomers different.
Z.
Isomers ಅಲ್ಲ isotopic. Isotopes means same jet different A. Isomer in a
Isobars, sir.
huh,
Sir, sir,
Isobars.
huh.
sir, ನನ್ನ ಫ್ರೆಂಡ್ ವಿಶ್ವೇಶ್ ಪಾಂಡೆ ಸರ್. Sir.
Okay.
Now he is in Tamil Nadu, sir. He is lecturer, and he willing to join the class, sir. Can you please
Yeah, sure, I
can you
will.
speak in English, sir, in this
And
class?
I discuss both Kannada and English. He understands Kannada or not?
No,
Okay.
sir, no, sir. He is from UP,
Okay.
sir.
Okay. 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 I will speak in English.
He can understand. Uh,
Okay. There. Mahesh. ಏನು ಹೇಳತ್ತಿ ಮಹೇಶ?
Sir, same different Z
Isobars. Oh,
isobars.
different. Not same ಬರ್ದೇನ? Here isobars are same A, different Z. That will be reverse, right? So here isobars are same A but different Zs. So they are isobars here we are going to define. Similarly, isotones, same number of neutrons. So it means same number of neutrons means how do you define this? For example, example are it is C14 and 6 and N15 and 7. So these are defined as a isotones. How? So if you see this atomic mass number is A equal to 14, Z equal to 6, isn't it? So if I take this A equal to 14 means A is actually defined as mass number is nothing but neutrons plus protons. Neutron plus protons. So number of protons is nothing but defined as a atomic number here. Therefore, atomic mass number becomes it is n plus z, isn't it? If I treat this n plus z here, then I am going to get here number of protons will be 8. So number of neutrons will be 8 here. And if you similarly if you check here, see that 15 and 7, 15, 15 and 7. So here I have the 7 is equal to z, right? Therefore, fourth number of neutrons in this case is also 8. Then here is also 8. Therefore, the same number of neutrons. The nuclei which have same number of neutrons they are defined as isotones. Similarly, isomeric nuclei. Isomers we define isomeric nuclei. Isomers. What do you mean by isomers here? Isomers are the nuclei which have same Z, same A, atomic mass A, but different intermolecular structures. But different intermolecular structures. Intermolecular structures. And their chemical behavior is going to be different. So these are called as isomeric nuclei. Similarly, we define about mirror nuclei, right? So mirror nuclei. How do you define mirror nuclei? So mirror nuclei is actually defined as like this. Means number of protons and neutrons will be interchanged. So number of neutrons and protons will be interchanged. Will be interchanged. So these are called as mirror nuclei. We call them as a mirror nuclei. See how do you define this mirror nuclei actually? Let us take an example. Example is lithium. Let us take this lithium. Lithium 3 with atomic number mass number 7. And similarly, there is another one is there beryllium. There is 4 with 7. So if you check this, once go to this number of atomic number is mass number is going to be 7. Then Z is going to be 3. For total number of protons, so protons will be 3. Then neutrons will be 4. And if you look at this, then here total A is equal to 7, Z is equal to 4, that is equal to same number of protons. Therefore, number of neutrons will be 3. If you look at this, 2 nuclei, so this 3 is the number of proton here, but the same 3 is the number of neutron here. Then here, we got that 4 number 4 is nothing but a Z here, but here 4 is nothing but a number of neutrons. So number of neutrons and protons is will be interchanged. P is equal to 3, N is equal to 3, here P equal to 4, and here N equal to 4. So these are called as mirror nuclei in the group. Here, remember that number of protons will be equal to number of neutrons in the both the nuclei. Therefore, if I treat, you see, if I take X and Y are two mirror nuclei. X and Y are two mirror nuclei. Let us take the X is defined as like this. So X is the nuclei with mass number A1 and atomic number Z1. Similarly, Y, let us take this is Z2, then this is A2. Okay. If we say this X and Y are mirror nuclei, become mirror nuclei. So mirror nuclei. So we are going to have a condition that here atomic masses should be same. Then relation between Z1 and Z2 is will be, so Z1 minus Z2 will be always plus or minus 1. Or you can treat that one as Z1 will be Z2 plus or minus 1 on the different model. So there will be only difference of 1 unit in both protons and neutrons of this mirror nuclei. And moreover, these nuclei have same radii but and different in the Columbian energies. Okay, so these are going to have the same radii. These nuclei have same nuclei, same radius, same radius. Okay, radius. Next is we discussed about next concept is about nuclear mass density. So we discussed about mass density. Just quickly, I'm going to revise all the concepts that we have discussed 2-3 days back. So we discussed about nuclear mass density. Nuclear mass density. So how do we define this nuclear mass density? Generally, see this nuclear mass density is given by rho is equal to mass divided by volume, right? So if you define this volume here, before going to this, we have even discussed about the nuclear size radius. Here only I am going to write that nuclear radius. Nuclear radius. So how did you define this? Nuclear radius is nothing but we know that nuclear size will be depending on its shape. Then that can be defined with a volume, right? So nuclear volume can be defined based on the atomic masses. So how much mass it is inside the nucleus, that is going to define about the volume. Means volume of the nucleus is always directly proportional to the mass which is present in the nucleus. Therefore, if you treat this volume like this 4 by 3 times of pi r cube as a, by treating that one as a sphere, then nucleus can be defined with volume that is 4 by 3 times of pi r cube. Then it will be treated as a directly proportional to A. From this we can see that the radius of the nucleus is directly proportional to A to the power 1 by 3. So why? Because the amount of the mass, that is nothing but nucleons, protons and neutrons. Right? Total mass which is present in the nucleus will be directly proportional to its volume. Therefore, we are going to define that R is directly proportional to A to the power 1 by 3, where that same relation can be written as R equal to R naught into A to the power of 1 by 3, where R naught is defined as a nuclear radius parameter, then that is defined as R naught is equal to, so R naught is value is going to be, R naught is nearly equal to 1.2 to 1.3 Fermi meter. Okay. So Fermi means 10 to the power of minus 15 meters. So that much range can be defined. And from this we can conclude that radius of the nucleus is directly proportional to the mass in 1 to the A to the power 1 by 3. Clear? Or cubic root of the mass number on the different. Then here we got that nuclear density is defined as mass divided by volume, right? So if I take this one as rho is equal to, if I define the mass of the nuclei, that is going to be, so there will be If I take the, for example, if I take this X is a nuclear with the atomic number Z, then mass number as A. So the total mass is defined as total number of protons plus number of neutrons. So if I take the random nuclei, that is going to be having, so it is going to have that Z number of protons is mass of the proton plus A minus Z times mass of the neutron is the total mass, then divided by volume of the nucleus is defined as, so here volume of the nucleus is defined as like this. So volume of the nucleus is going to be, it is 4 by 3 times of r cube. We know that r is equal to, that we know that r equal to r naught, right, from this relation that I have already, right, from this relation if I substitute that, rho is equal to, generally see mass of the proton and mass of the neutrons will be almost the same. That if I treat mass of the proton is nearly equal to mass of the neutron, then I can define this one as like this: Zmp plus E times of Zmn minus Z times of Mp. If I make these two equal, then these two get cancelled right here. Then 4 volume is defined as 4 by 3 times of only pi r cube. Now r cube can be defined as r naught into e to the power 1 by 3, r naught into e to the power of 1 by 3, then whole power 3, that is cube. Then I'm going to have only like this. Density, nuclear density is going to have, there is mass number into its mass of the neutron or proton. Generally we define this one as a mass of the nucleon, because nucleons are protons and neutrons only. So generally we treat that one as mass of the proton is equal to mass of the neutron is equal to, that is defined as mass of the nucleon. Mass of the nucleon, this is defined as mass of the nucleon. Mass of the neutron. Therefore, here it is defined as A into mass of the neutron divided by, that is 4 by 3 times of pi r naught cube. That is into, A becomes only A, right? Therefore, if we get these A and A get cancels, then we left with only rho is equal to mass of the nucleon divided by 4 by 3 times of pi r naught cube. See, Mn mass of the nucleon is constant, 4 by 3 pi is constant, r naught is also constant. Therefore, density of the nucleus will be always constant. That will be defined in the range of 10 to the power of 17 kg per meter cube. 17 kg per meter cube. The nuclear density is independent of its volume. It is constant for all the nuclei. So it is not, the nuclear density is not dependent on volume, hence as its volume is depending on the atomic mass number A, therefore density is independent of independent of mass number. So it will be always constant for all the nuclei. So nuclear mass density, this is defined as rho. Nuclear mass density is constant for all nuclei, right? All nuclei. So that we have discussed in the previous class. And similarly, we discussed about nuclear charge distribution also. So nuclear charge distribution. So in the previous class we discussed about nuclear charge distribution. Nuclear charge distribution. So here nuclear charge distribution is actually given by Fermi model. Okay. So according to the Fermi model, and moreover you should remember that charge distribution inside the nucleus is not uniform. So charge distribution inside the nucleus is not uniform. Uniform means, so it is not going to spread uniformly throughout the volume of the nucleus. So it is going to vary. So it remains constant up to a certain range, and after that it is going to fall off. Therefore, according to the Fermi model, Fermi model. So we define that nuclear charge distribution will be defined like this. It is going to be rho is equal to rho naught divided by 1 plus e to the power of some k constant into r minus c. So where rho naught is nothing but a central charge density. So where rho naught is defined as central charge density. I am going to define about the charge, not the mass density. Remember here it is about charge density. So rho naught is defined as central charge density. Central charge density. And where this r is nothing but r is defined as a radius, distance. R is now here is going to be distance. Where c is nothing but, so remember this c is very important. C is nothing but distance from center of which the density falls, distance from the center. So wait a second. So distance from the center where its density falls, its density falls to 50% of central charge density. Central charge density. So see here I will define this through graphically. So it is defined like this. Moreover, this C value is going to be given as C is equal to 1.07 into 10 into a to the power of 1 by 3 Fermi meter. So it is defined similar to the radius of the nucleus. Remember, this is the formula to define the central or charge distribution in the nucleus. If you treat this one as a nucleus, and if you take this one as a nucleus, so this is the center from the center of the nucleus. From here to here, if I define this one as a radius r, okay, so any constant radius. But as there are protons and neutrons are there, so if you look at the charge distribution inside this one, it is not uniform throughout this volume of the nucleus. So it is going to vary from center to the outside. So and when it is not constant even at the edge. It is going to slowly fall off. Okay? So that is defined with this graph. So generally we define this one as like axis will be treated as density, then x-axis is treated as a distance r. So this is along this direction, along y direction. Then this graph is given by like this. So it will be constant for some region. Then after that, it going to fall off slowly. So this is the graph that expression can be. This expression is going to explain it. Okay. So here, see density here it is going to be constant, and if it is at the distance r equal to 0. So at distance r equal to 0, it is nothing but it's the center of the nucleus, right? Center of nucleus. So at center of nucleus, the density is going to be constant. So when you go from the center to the outer edge of the nucleus, then it will be, for some reason it will be constant. After that it goes to fall off slowly. So where density becomes 50% of its central density. 50% of central density means, so here center it is rho naught. For distance at which density becomes rho naught by 2, then this distance is defined as c here. So that's why I defined the c. C is nothing but it's a distance from the center where its density falls to 50% of the central charge density. Then the distance is defined as a c here. Okay, this is the graph. They may ask the direct graph only. They may ask based on the expression. Remember, this expression is very important for the charge distribution. It is defined as a Fermi model. Okay. And similarly, we defined about binding energy. Right? In the previous class, I have defined about the binding energy of the nucleus. Defined as binding energy of nuclei. So how do you define the binding energy? So binding energy is the amount of the energy required to break its components or it is the energy required to build the nucleus by its components. That is defined as a binding energy, which is the energy with which all the nucleons are going to bond within the nucleus. That is defined as the binding energy of the nuclei. Especially here, this MP is defined as the mass of the proton. In this case, mass of proton. Here Mn is defined as mass of neutron. Then generally we define any nuclei with its atomic number Z and mass number as A. Then generally by looking at nuclei, we are going to define theoretical mass for it, calculated mass. So theoretical mass of nuclei, that is X, is going to be defined as, so Z times the mass of the M proton plus there will be A minus Z times of neutrons will be there. So that is going to give us a theoretical mass of that nucleus. Here, see, remember this, A is going to be its sum of Z plus N. Therefore, N is equal to, define that as A minus Z, isn't it? So that is the main. So here we are going to define that theoretical mass of the nucleus. But observed mass is found to be less than the theoretical mass. Actually, practically observed mass is actually lesser than its theoretical mass. Therefore, we define that one as a observed mass only. So, observed mass. Practically observed mass is going to be defined as m observed, but it is always less than. It's always less than its theoretical mass. So generally, by taking its number of photons and number of neutrons, we are going to define the mass. That is by calculate. This is a calculated mass. Okay, it is calculated mass. So, but actually, if you observe practically, then mass will be different than calculated mass. Therefore, there is a difference between this observed mass and theoretical mass. The difference is defined as mass defect. Therefore, I will take this one as a mass, theoretical mass and observed mass. Therefore, the difference between these masses, it is delta m is equal to mass is theoretical minus mass observed. So this mass difference is defined as mass defect. Okay. So here mass, theoretical mass and observed mass. Generally, if you take, see, observed mass will be directly given in the problem. So only theoretical mass we need to calculate. If you take the difference between these two masses, then you can define the mass defect. According to the special theory of relativity by Einstein, so we define the binding energy as is equal to delta m into c square. The mass defect into speed of the light square is defined as binding energy. So it will be defined by Einstein, right? Delta mc square. Delta m is defined as mass defect. So this is from special theory of relativity, STR. We define that one as STR. Therefore, the binding energy is defined as, there is a mass difference will be there between observed mass and its theoretical mass. Then the binding energy is defined as delta m into p square, because he is going to explain that mass is going to be converted into energy, and energy is going to be converted into mass. So that is the main concept behind Einstein theory. Now, by using the same thing, you can define the binding energy as like this. That is, binding energy is equal to, there is observed mass is given by, that is theoretical mass is given by Z into mass of the proton plus A minus Z times of the mass of neutrons minus, there is mass of observed mass. So I will define this observed mass as like this, A with Z, that is observed. Okay, then into C square, because this is going to be the delta m, right? So delta m is equal to Z into mp plus A minus Z into mn minus mass, observed mass of the nucleus. Here, see, the problems, if they have given mp, then treat this one as observed mass of the nucleus. So it's the nucleus or mass of the nucleus. Mass of the nucleus. This if MP is given. Sometimes in the problem they may give one as mass of the hydrogen. Sometimes they may give this one as a mass of the hydrogen. How? If you are going to calculate the binding energy of the nucleus, so this is binding energy of nucleus. Use all the components of the nucleons only. But sometimes in the problem they may give, so instead of mass of the proton, they may give mass of the hydrogen in this part. So that will be converted into atomic mass than nuclear mass. Okay. Therefore, that can be converted like this. So binding energy is actually given by that is Z into MP. Okay. If I want to convert this one into the for the atoms, then only difference between nucleus and atom is number of electrons. Then we can add the same number of electrons into this mass of the proton, right? We are going to get the total mass of atom. Therefore, Z into mass of the proton, then plus Z into mass of the electron, then it is going to give us a total atom. Then plus A minus Z times mass of the neutron. This will be the total new atom, right? Then minus, then see I have added this mass of the electron, right? So let's subtract the same thing because there should not be any difference between this formula and this one. It just is a conversion from nuclear mass to atomic mass. Therefore here Z into MP, Z into Me, then A minus Z times of mass of the neutron, then minus times. So it is observed mass of nucleus, observed mass of the nucleus plus its electron masses. Then it is multiplied with T square. So here it's observed mass of the nucleus plus observed mass of that electron. So observed mass of the nucleus along with the electron is defined as observed mass of atom. So that is defined as A with Z, same A with Z. M is now defined for atomic mass. Atomic mass. In the problems, if they give like this, then it will be defined as atomic mass. Then if they have given only mass of the proton, then take that mass of the nucleus. See here, it's mass of the proton plus mass of the neutron. Mass of the proton plus mass of the electron. It's generally defined as Z times mass of the hydrogen. Mass of the hydrogen, because hydrogen, if you look at the hydrogen atom, it is going to have only proton inside and one electron outside. There is no neutron in this hydrogen atom. So if you are going to treat this mass of the proton plus mass of the electron, treat that one as generally mass of hydrogen. Mass of the hydrogen. So if you multiply that with the Z, then according to that element, if you take the new lithium, sodium, whatever it may be the element, if you multiply Z with it, then it is going to give the total mass of the protons and electrons in that particular nuclei. Therefore, generally only the mass of the proton, mass of the electron is defined as mass of the what is this? Hydrogen. Okay. Then I will rewrite the same equation as Z into mass of the hydrogen plus A minus Z times mass of the neutron minus, so it is now replaced with that is atomic mass A with Z with this into C square. Then that gives total binding energy of the nuclei in terms of atomic mass. Okay. So if they give the total atomic mass, then take this mass of the hydrogen here. Okay. So it will be treated for the atomic mass. Done with this? This is defined as the binding energy. You see, binding energy, same binding energy can be defined with binding energy per nucleon also. Binding energy per nucleon. How do you define the binding energy per nucleon here? What do you mean by nucleon? Nucleon is nothing but a total number of nucleons. That is nothing but A. Nucleon means protons plus neutron. So that is going to be A. So here binding energy per nucleon is going to be, such as binding energy per K. So if you take the ratio of its binding energy with atomic mass, then it is going to be defined as binding energy per nucleon. It is used to measure the relative stability of a different nuclei. Remember, it is used to measure binding energy per nucleon used to is used to measure the stability of relative stability of different nuclei. Different nuclei. So more is the binding energy per nucleon, more will be the stability. Remember this point. So if more is the binding energy per nucleon, more will be the stability. More will be the stability. Okay. So this is what the binding energy of the any nucleus can be defined. So once if you calculate the binding energy, divide it with its mass number, then you are going to get the binding energy per nucleon. Based on the binding energy per nucleon, so we are going to differentiate all the elements by its by a graph. It is defined as binding energy curve. So we usually call that one as binding energy curve. Binding energy curve. Okay. So this one you have already, I think, studied. Everyone have studied all this, right? So the graph is defined as here binding energy curve is going to be for binding energy per nucleon versus its mass number or nucleon. So it is a mass number. Okay. And that graph is going to be like this. Wait a second. I'll paste it. Yes. Once look at it. Okay. So the graph between binding energy per nucleon versus its mass number. If you go from the first elements like from hydrogen to helium, lithium, beryllium, carbon, all the noble gases, up to heavier nucleus like uranium. So if you plot the graph for binding energy per nucleon, we are going to take the graph like this. Here, from this the lowest element will be defined as the hydrogen here, that is with uh, only z equal to 1, then even a is also equal to 1. If you go from hydrogen to all the heavier nucleus, this graph will be defined like this. Okay. I will give the features for this graph. It shows peaks corresponding to, especially see, you can see the peaks here. Here one point is there, here one point is another point here, here. All these are going to be defined as a peaks. True shows peak corresponding to the atomic mass numbers A equal to 4, 8, 12, 16, 20. So, see, the first feature of this graph is curve shows peaks at A equal to 4, 8, and 12, 16, 20, like this. See, 4 is nothing but helium, right? Then 8 is nothing but beryllium. Yes, beryllium. Then 12 is nothing but carbon. Then, so right, 16 is nothing but oxygen. So these are the graphs. So particularly here will be helium, here it is going to be beryllium, then carbon, then nitrogen. These are the peaks. So the atomic numbers which are less than atomic mass numbers which are is less than 20. This means they are more they have the stability corresponding to their neighbors. If you look at this 4, then if you look at 8, 12, 16, 16 is more stable than 12. 12 is more stable than 8. 8 is stable than 4. Their stability is going to increase by their peaks. These are the elements which are there actually stable only. Compared with their neighbors, they are stable, but they are not the most stable. So remember, so here we can see that in these graphs, binding energy per nucleon versus mass number graph, you can see A is less than or equal to 20. There you can see the peaks in the graphs. Peaks in the graphs. They are stable with corresponding to their neighbor nuclei. Okay, so this is due to the. Moreover, if you look at this helium, beryllium, boron, carbon, and all these things, they are going to have even nuclei form. Means two number of protons, two number of neutrons. See, helium is nothing but 2 with the 4. If you look at the carbon 6, 12, right? Oxygen 8, 16. If you look at this, in these all the elements, you can observe that two number of protons plus two number of neutrons. Here also, two number of protons, two number of neutrons. So it means equal numbers. My meaning is equal numbers. So if you look at this, number of protons plus 8 number of neutrons. Here 6 number of protons, then 6 number of 6p and 6n. Then here also if you look at this 2p and 2n. So these type of nuclei are defined as even nuclei. So we call that them as even nuclei. Especially these peaks will be observed for even nuclei. Even nuclei. After these elements, you cannot see even nuclei form. Means same number of protons, same number of neutrons. Okay. Therefore, so if the number of protons and number of neutrons are multiple of 2's, then 2p and 2n format, and they are defined as even nuclei. According to the stability concept, the nuclei which have even nuclei format, they will be more stable among all the nuclei. Okay. Then second feature of this graph is going to be, if you look at the atomic masses which are greater than 20 but less than 120. So it is defined as here it is here they are given 118 they are given. Generally we treat them as from A less greater than 20, then A less than 120. Binding energy per nucleon is almost constant. If you look at this if you look at from nitrogen to up to here, this part is not much varying here. So it will be more constant graph. Therefore, from the nuclei in the range of atomic masses E greater than 20, see I will write here for nuclei in the range A is greater than 20 but less than 120. But A less than 120. The binding energy of nucleon is roughly constant. Okay, roughly constant. So they are almost in the range of 8.5 mega electron volt. Okay, so they are in the range of 8.5 mega electron volt. So it will be defined as the energy. So if you look at this part, this average energy is going to be defined as 8.5 mega electron range. In that part, the atomic masses which are greater than 120 and less than 120, they are going to have almost saturation of property of nuclear forces. There, they are going to have. So by looking at this graph, as their binding energy per nucleon is all roughly constant, then this property of these nuclei are called as saturation property. Saturation property. What do you mean by the saturation property? Saturation property means they are almost stable one. Then the nuclear forces are saturated. We define based on the nuclear forces. Nuclear forces are saturated. Saturated means they are inert to react. They are stable, more stable. Okay, so the saturation property means nuclear forces are stable forces. Okay, therefore we define that as saturation property. Generally, saturation property is nothing but A particular nucleon interacts with limited number of its neighboring nuclei or nuclei, not with all the nuclei. And if you look at this, if you go to atomic numbers from A equal to 20 to A equal to 120, there you can observe that almost all these nuclei are less reactive. Less reactive. They are not completely inert, they are less reactive. So that is the property is defined as saturation property. A particular nuclei interacts with only limited number of its neighboring nuclei. So interaction will be only with interaction will be only with limited number of nuclei. Limited number of nuclei. Nuclei. So not with all. Not with all nuclei. So that property is defined as saturation property. Moreover, these nuclei are going to interact through electromagnetic interaction. Generally, this binding energy per nucleon is going to be defined like this. So as there are binding energy per nucleon or binding energy is always directly proportional to A into A minus 1 by 2. Okay. According to the saturation property, we are going to define that as binding energy will be directly proportional to atomic mass into its minus 1 divided by 2. This is the actually rule, because as they are going to increase their nucleons mass number, they are going to get more stability with their nuclear forces. So nuclear forces will be almost they'll be in binded state. So if you look at this nucleus, see, if you look at the nucleus, nucleons which are present in this nucleus are going to be bound within the nucleus as their mass number is going to increase. According to this concept of saturation or concept of increase in the nuclei, so we generally define this binding energy per nucleon is always directly proportional to its mass number. As mass number increases, their stability becomes more, means they get more stable. So according to that concept, we define that binding energy is directly proportional to like this. Then if you take the binding energy per nucleon, we define that one as A minus 1 by 2. So if you look at this just equation here, even though it is A minus 1, it will be a number only, just number only. There will be only one difference will be there. So if you look at this binding energy per nucleon, it's directly proportional to atomic mass. If you look at this, the binding energy per nucleon is very linearly with A. So as per the concept, so as if you go on adding the neutrons into the nucleus, so it must get more stable. It must get more inert to the interactions. According to this, we generally define that graph as like this. See, if you go according to this graph, means linearity with A, then we get for binding energy per nucleon versus nucleon. Initially, the hydrogen from hydrogen to helium, helium to carbon, carbon to nitrogen, like this it appears when A is less than 20. After that, if you increase the nucleons, it should directly increase like this, right? Linearly with respect to atomic mass. But actually, observed graph is like this. So whatever I have pasted above, so this is the observed graph. But according to the theory, so we define that one as, so as we are increasing nucleons, its a mass number, sorry, binding energy per nucleon also get more and more value. As binding energy is more, then automatically then those nuclei are defined as more stable. But in practical, it is not like that. So it is the property of linearity. So binding energy variation with respect to A, it is going to deviate. That deviation is defined as, so if you go on increasing or if you go for a higher atomic mass numbers, then their stability is going to decrease. If you look at this graph, what happens there? See, especially elements which are less lesser than, like iron is defined as a more stable one. I will define that. Then I will go to the instability of the heavier nuclei. Here, maximum B by A, that is nothing but binding energy per nucleon, is corresponding to the iron Fe56, which is almost 8.8 mega electron volt. See, so iron is the most stable one element according to the binding energy concept. That is, it is going to have 8.8 mega electron volt. This I have told that 8.5 is average of all the nuclei which are their binding energy per nucleon was almost roughly constant. Especially for iron, it is defined as 8.8 mega electron volt. So maximum binding energy is per nucleon is for iron 56. Okay, iron 56 is more stable than any element, more stable one. It doesn't mean that it is not a reactive. It reacts with all the limited number of nuclei. So their energy is defined as 8.8 mega electron volt. See, as you go on increasing the nuclei, as I told that. So in case of the nucleus, if you go on adding the nucleons, so means if you add the nucleons, means you are going to increase in mass number. As mass number increases, their stability of holding the molecules, so holding the nucleon within its bound range, is going to decrease. See, if you go on adding the nucleons here, the energy is defined as a binding energy. What is that binding energy? So it is the energy with which it can hold all the nucleons within its boundary. Right? So then it will be defined as a more stable one. So it is defined as a stability, stable one. But what happens here? If you go on adding the nucleons, their size is going to increase again. Volume is going to increase. As their volume increases, its stability to hold all the nuclei is going to decrease. That's why the nucleons having A greater than iron, greater than Fe56. The binding energy falls due to the binding energy falls due to the decrease in the due to the decrease in their stability. So why stability decreases here? Because of the more number of nucleons. So it cannot hold all the nucleons with the same energy. As you go on increasing the atomic nucleons into it, nucleons if you are adding nucleons means it doesn't mean that, so it means that its atomic mass number is going to increase. So therefore, according to the graphical part also, even according to the their size property and their stability property. So there, as the nucleons which are going to have here they have written, see, elements heavier than iron can yield energy by nuclear fission. Especially, so we define lighter nuclei is going to give us a heavier one, that is defined as a fusion. Then heavier nuclear is going to divide into two parts, divide into two lighter nuclei, then it's defined as a fission. So remember, the atomic masses which are greater than iron, they are going to yield fission. They are going to go through the fission process. Here it will be fusion, because lighter nuclei form the heavier one, heavier nuclei form lighter one. That is by the fission and fusion process. Fine. And
Sir, even electromagnetic force dominates the nuclear force also, sir.
yes, that dominates. Why there will
If
be
we add the
domination of
more number of nuclei.
electromagnetic force than nuclear? Do you know that? That is an increase in the
Because
number
of
of charge distribution will be
increase in
increases.
number of
So they
protons, sir.
repel each other because of the same charge. Then the electromagnetic interaction is going to dominate. Therefore, nuclear force decreases, then their stability falls down. This is also one of the reasons. Okay. So this is what actually we defined for the binding energy part. Okay. Remember, there is another one concept. That is, you see, lighter nuclei are almost even nuclei. What do you mean by even nuclei? Means same number, means even number of protons and even number of neutrons. They are defined as even nuclei. Okay. So almost lighter nuclei are lighter nuclei are even nuclei. So even nuclei, even nuclei. And moreover, these are abundant in nature. Remember, these are abundant in nature. Most abundant elements. Most abundant element. Abundant element. Okay. These are lighter nuclei. So, and moreover, see, if you look at this most abundant property of all the nuclei, it's going to tell us that nature prefers even system. So this is the property of the nature. So nature prefers to even part, even system. Okay. Therefore, the most abundant elements on the Earth crust or in the atmosphere of Earth are even nuclei only. Okay. And moreover, they are lighter nuclei. Next part is so. Moreover, it's even elements, even element are most stable nuclei. And here, even and even odd and odd even nuclei are moderately stable, moderate stability, moderate stability. So where in case of odd nuclei, the odd number of protons and odd number of neutrons, so they will be least stable one, least they are going to be least stable, Okay. So generally, see, as if you look at the stability curve of the nucleons. So let us discuss about the stability curve. If you look at the stability curve of the nucleons, that is, if you look at the graph for a number of uh, neutrons versus number of protons, that is the graph number of protons versus number of neutrons, Okay. See, we know that even means equal number of protons and equal number of neutrons means then we generally have the graph like this, right? So this should be the graph because linear graph is going to tell us about same number of protons. If you have them, so if you have 20 neutrons here, if it is going to have 20 only, then it is 40. If it is 40, 40, so that graph will be linear. That is even part is there. Okay, but actually what happens, as we have discussed here, the above part, lighter nuclei and almost lighter nuclei are beginning elements of the periodic table, right? So we are going to have less number of protons and less number of neutrons. Almost all lighter nuclei are going to follow up this graph. Lighter nuclei are going to follow up this graph. This graph is called as a stability curve. So this reason is this graph is called as stability curve. Okay. According to the prediction, that if all the elements are stable element, then the graph should be a straight line which is passing through the origin of the graph, like graph of number of protons versus number of neutrons. If there are equal number of protons or equal number of neutrons, so almost elements will be stable. If you go to the periodic table elements, then hydrogen to helium, lithium, all these elements, almost all lighter nuclei have equal number of protons and equal number of neutrons. But if you go to the elements which are greater than 20, so for example, if I take this graph, I will define Z is equal to 20. A equal to 20 means Z equal to 10, right? So if I take that E is equal to E is greater than 20. For E is greater than 20, then the elements that are coming, they are going to have more number of protons and more number of neutrons. They are going to deviate from this stability graph. They are going to deviate like this. That curve is going to be, this is a practically observed curve. So this is theoretical curve. So theoretical one means according to their stability, it will be straight line. But if you look at all the graphs, all the elements in the periodic table, that curve is going to be deviate from its original stability graph. So that's why we define this one as deviated curve. We call this one sometimes called deviated curve, or we call even we can call that one as stability curve only. But this part, this range, this range is defined as from here to here. This range is actually stability region. So this range is defined as, or this region is defined as stability range, stability region, stability region. The elements which are lying in this part, see, there are a lot of elements will be located here. We will paste that one graph from yes. Look at this graph here. See, stable isotopes and unstable isotopes. Reds are unstable isotopes. Actually, blue dots are stable isotopes. Actually, here should be the originality. As I told, line of stability follows Z is less than 16. So if you go to the elements which are less than this lighter nuclei, see helium, carbon, oxygen, they are going to follow the straight line. But when you go to the higher nuclei, then they are going to deviate. Okay. So this is what exactly the deviation from its stability curve.
Sir,
Unequal
no, sir, why it
number
deviates?
of protons and neutrons when you go to the higher nucleus.
ಮತ್ ಸರ್ ಇನ್ನೊಂದು ರೀಸನ್ ಸರಿ ನಾವು ನಲಿಫೈ ಮಾಡ್ಬೇಕು EM ಇಂಟ್ರಾಕ್ಷನ್ ಎಲೆಕ್ಟ್ರೋಮ್ಯಾಗ್ನೆಟಿಕ್ ಇಂಟ್ರಾಕ್ಷನ್ ನಲಿಫೈ ಮಾಡ್ಬೇಕಂತಂದ ನ್ಯೂಕ್ಲಿಯರ್
That
ಫೋರ್ಸ್
is due
ಡಾಮಿನೇಟ್
to
ಮಾಡ್ಬೇಕಂತ
ಯಾವಾಗ
ನ್ಯೂಟ್ರಾನ್ಸ್
ಆಗ್ತದೆ
ಆಡ್ ಮಾಡ್ತೀವಿ ಸರ್.
ಈ ಬೀಟಾ ಡಿಕೆ ಅಂಡ್ ಬೀಟಾ ಪ್ಲಸ್ ಡಿಕೆ ಬೀಟಾ ಮೈನಸ್ ಡಿಕೆ ಆಗ್ತದೆ. ದಟ್ ನಾನು ಹೇಳೋದು get stability, more stability, they are going to get deviated from the stability graph, right? To get more stable, they are going to go under two decay process. One is beta minus, another one is beta plus decay. The elements which are lying, see, if you look at this graph, the elements which are lie above the stability region, generally we call this one as a stability region, right? Elements which are lying here, so if they are lying above the stability region, they are going to decay through beta plus process, so the beta minus decay. So these elements are going to have they are going to stability by beta minus decay, and these elements are going to get stability by beta plus decay. That is the main that is interaction, what we call interaction or process. Interaction process, we can call this one as an interaction process. So to get more stability, there will be two processes. One is defined with the beta minus process and another one is beta plus process. So what happens here? Beta plus process ಒಳಗಡೆ proton is going to convert it into, in this beta plus process, proton is get converted into neutron plus positron, where in this case neutron is going to convert into proton plus electron. So only reason to get conversion from neutron to proton, proton to neutron is to get the nuclear stability. That's the point. To get nuclear stability. Okay. ಇದನ್ನ ಹೇಳತ್ತಿದ್ದಿಲ್ಲ ನೀನು?
ಅದು ಸರಿ. ನಾ ನ್ಯೂಟ್ರಾನ್ ನಂಬರ್ ಯಾಕೆ ಜಾಸ್ತಿ ಇರ್ತಾವತ್ತಂದ್ರೆ ಸರಿ ಹೈಯರ್ ಹೋದಂಗ ಬಿಕಾಸ್ ನಾವು EM ಇಂಟ್ರಾಕ್ಷನ್ ನಲಿಫೈ ಮಾಡಾಕ ನ್ಯೂಟ್ರಾನ್ಗಳು ಆಡ್ ಮಾಡ್ತೀವಿ.
ನ್ಯೂಟ್ರಾನ್ಗಳು ನಾವು ಆಡ್ ಮಾಡೋದು ಹ್ಮ್
ಈಗ
ಹಾ
ನಮ್ದು
ಅದನ್ನ
ಗ್ರಾಫ್
ಹೇಳತ್ತೆ. ಹ್ಮ್
ನೇಚರ್
ನೇಚರ್
ಆಡ್
ಆಡ್
ಮಾಡೈತ್ರಿ. ಹಾ ನಾವು ಆಡ್ ಮಾಡಿ ಅಂದ್ರೆ ನೇಚರ್ ಆಡ್ ಮಾಡೈತಿ.
ಅದ್ರ ಮೀನಿಂಗ್ ಏನು ಗೊತ್ತಿಲ್ಲ ಇಲ್ಲಿ. Same, if you go to the in this graph, if you go to the higher nucleus, see, this graph is going to deviate towards the neutron part. Right? This is a observed one. ಇದು ಆಕ್ಚುಲಿ ಇರೋದಿದು. ನಾವು ಥೆರಾಟಿಕಲಿ ನೋಡಕ್ ಬಂದ್ರೆ ಈ ತರ ಗ್ರಾಫ್ ತೋರಿಸ್ಬೇಕದು. ನಮ್ ಅಂದ್ರೆ ರೂಲ್ ಪ್ರಕಾರ ಸೇಮ್ ನಂಬರ್ ಆಫ್ ಪ್ರೋಟಾನ್ಸ್ ಸೇಮ್ ನಂಬರ್ ಆಫ್ ನ್ಯೂಟ್ರಾನ್ಸ್. ಮುಂದೆ ಹೋದಂಗ ನ್ಯೂಟ್ರಾನ್ಸ್ಗಳನ್ನ ತಾನೇ ಆಡ್ ಅಪ್ ಮಾಡ್ಕೋತದೆ. ಅದನ್ನೇ ಹೇಳತ್ತಿದೆ ಪಾಯಿಂಟ್. ಇಲ್ಲ, it is going to get deviated towards the neutron number and protons. Only to, I mean, that is the reason, that is to decrease its electromagnetic interaction than nuclear interaction, nuclear force. If that nuclear force is strong, then automatically that element will be more stable. That is the point, right? Okay. ಮತ್ತೇನ್ ಪಾಯಿಂಟ್ ಅದ ಇದ್ರಾಗ? So Z less than 20, stability curve coincides with n equal to Z. See, if you look at this part, here, from here to here, this part is going to be n equal to Z. So if you go higher higher elements, Z is greater than, actually it is defined as 16 here. So generally we can define even as 20 also. So Z greater than 20, it is going to deviate from that n equal to Z. This graph is called as n equal to Z line. And this is up here, it is going to follow, later it is going to deviate. According to the nature, ಏನಿಗೆ ಬ್ಲೂ ಡಾಟ್ಸ್ಗಳು ಕಾಣ್ತಾವಲ್ರಿ ನಿಮಗೆ, ಇವೇನು ಬ್ಲೂ ಡಾಟ್ಸ್ ಕಾಣ್ತಾವಲ್ಲ, this is actually the stability graph according to the nature. So the elements which are lying in this graph, they are going to be more stable with the nuclear forces. Is that clear? Especially in the part of KSET, I'm going to ask only this part, graphical part, and what is the nature of the graphs. Remember that what I told, beta plus decay and beta minus decay. The nuclei lying above the stability region have tendency to beta minus decay, and elements which are below the stability line are going to possess beta plus decay. And moreover, ratio for the stability, higher element, n divided by p ratio, n divided by p ratio for stable nucleus, for stable nuclei is nearly equal to 1.7 ratio. For lighter nuclei, it is always n equal to Z. If you go for the higher nuclei, n by p. If it is p by n, then it will be reverse, right? Because more number of neutrons will be present than protons for the higher nuclei. So this is what the concept of this binding energy per nucleon, and their stability based on the binding energy part. Now, one second, I will see the syllabus. In the previous parts that I have covered, like things I have covered in the particle physics is elementary particles I have covered, is already done. Their quantum numbers also done, charge, spin, parity, iso spin, strangeness, everything I have covered. Riemann-Nishijima formula covered, Cork model, Grignon's meson, CPT, invariance I covered. Applications of symmetry arguments to the particles not covered, but parity and non-conservation of weak interactions I have covered. So only this much part is done. Relativistic kinematics that I will look at later. Then now I started with the nuclear part. I have covered here basic nuclear properties like say size, shape, charge distribution, spin, parity. Spin and parity I have already covered in the same part. Binding energy I have done. Now semi-empirical mass formula. So now let us start with the semi-empirical mass formula. Then we will go to the liquid drop model. Then nature of nuclear force in form of nucleon potential, charge independence and charge symmetry of the nuclear force, neutron problems, evidence of the shell structure, shell model, is its validity and its limitations, rotation spectra, alpha, beta, gamma decays, their selection rules, and fission and fusion part. Now, next part is about semi-empirical mass formula. Semi-empirical mass formula. Now, what do you mean by semi-empirical mass formula? Now is semi-empirical mass formula. ಆಕ್ಚುಲಿ ಇವತ್ತೇನು ಕವರ್ ಮಾಡಿದೆ ಅದು ಲಾಸ್ಟ್ ಕ್ಲಾಸ್ ಒಳಗೆ ಆಗಿದ್ರಿ ಅದನ್ನು ಮತ್ತೊಂದು ಸತಿ ಸ್ಟಾರ್ಟ್ ಮಾಡಿ ಬಿಕಾಸ್ ಮತ್ತಾಗಿ ನಾನು ರೆಕಾರ್ಡ್ ಮಾಡ್ಕೋತ ಕೊಡ್ಬೇಕು ನಾ ಇದನ್ನ ಯಾವುದೋ ಎಲಿಮೆಂಟ್ರಿ ಪಾರ್ಟಿಕಲ್ಸ್ದು recording parts of that I will do later that one and I will revise that one later. Okay, now nuclear part is going on. ಹಾಗೆ ಸ್ಕಿಪ್ ಆಗಬಾರ್ದಂತೆ ಇದನ್ನ ಸ್ಟಾರ್ಟ್ ಮಾಡೀನಿ. ಆಕ್ಚುಲಿ ಇವತ್ತು ಸ್ಟಾರ್ಟ್ ಮಾಡ್ಬೇಕಿತ್ತು, ಕ್ಲಾಸ್ ಚಾಲೂ ಮಾಡ್ಬೇಕಾಗಿದೆ, ಇಲ್ಲಿಂದ ಚಾಲೂ ಮಾಡ್ಬೇಕಾಗಿತ್ತು. ಸೆಮಿ ಎಂಪಿರಿಕಲ್ ಮಾಸ್ ಫಾರ್ಮುಲಾ ತಿರುಗಾಡೋದು ಎಲ್ಲ ಮುಗಿತಾನ ಸುನಿಲ್ಲ. ಒಂದು ವಾರ ಕ್ಲಾಸ್ ತಗೋತಾನಂದ್ರೆ ಲಕ್ಷ ನಿನಗೆ ಕ್ಲಾಸ್ ಬಿಡ್ತೀವಿ ಅಂತಂದ್ರೆ ಫುಲ್ ಖುಷಿ ನಿನಗೆ. ಎದಕ್ಕೆ ಬೇಜಾರಾಕತ್ತೆ?
ಇಲ್ರಿ ಸರಿ ಬೇಜಾರಾಗೈತಿ.
ಕ್ಲಾಸ್ ಬಿಡ್ತನಲ್ಲಿ ನೀನ್ ನಾನು ಕ್ಲಾಸ್ ತಗೊಂಗಿಲ್ಲ ಅಂತ ಹೇಳ್ತಿದ್ದೆ. ಇವನಿಗೆ ತಿರ್ಗಾಡ್ಕೊತ ಹೋಗ್ಯಾನ ಪಟ್ಟದಕಲ್ಲು ಬಾದಾಮಿ ಅಂತ. ಓಕೆ,
ಮೈಂಡ್ ಫ್ರೆಶ್ ಮಾಡ್ಕೊಳಕ್ ಸರ್, ಪ್ರೆಷರ್.
ಓಕೆ, ಇದು ಸೆಮಿ ಎಂಪಿರಿಕಲ್ ಮಾಸ್ ಫಾರ್ಮುಲಾ. ಏನಿದು ಸೆಮಿ ಎಂಪಿರಿಕಲ್ ಮಾಸ್ ಫಾರ್ಮುಲಾ? See, binding energy at the end defined ಮಾಡಿದ್ರಲ್ಲ ನೀವು. This binding energy is not just a formula to by using mass defect. There are a lot of energies that are going to form the total binding energy of the nucleus. They are, so here we know that binding energy, but this binding energy is going to constitute different forms of energies. Different forms of energy. They are, first one is volume energy form. That is, first one is volume energy. So the total binding energy is going to be constituted by its volume energy also. The volume energy is nothing but taking the nucleus to be spherical as in the liquid drop model. So we are going to have a energy term for the volume part. So by treating the nucleus as a spherical part, spherical in nature, treating the nucleus as a spherical in shape or spherical in nature. So volume energy is defined as, see, volume is always directly proportional to atomic mass number. You know this. Therefore, volume energy is defined as volume energy is always directly proportional to its volume. By using these, we are going to define that volume energy is always directly proportional to 4/3 times of KR2. As it is going to have a more number of nucleons, so its energy will be more. That is, volume energy is generally termed as. Therefore, here the volume energy is directly proportional to. Can I write this one as A only? Just can I write like this? Because 4 by 3 times of P, R can be written as R naught into E to the power of 1 by 3 whole power 3. Therefore, this becomes only 4 by 3 times of P R naught cube P. Therefore, here directly proportionality is going to be only A. Therefore, this volume energy of the nucleus is defined as AV into A. What is this AV here? AV is defined as volume energy constant. So AV is defined as volume energy constant. So energy possessed by the nucleon or nucleus due to its volume is defined as volume energy. Here similarly we are going to define the surface energy also. Second one is surface energy term. So means the total energy is going to have a different terms or different forms of energies. It is totally constituting the binding energy. The second one is surface energy. Surface energy. So we sometimes we call this one a surface energy term. All these are terms only. That energy is going to have different forms of energy terms. So that is one is volume energy term, another one is surface energy term. All the nucleons inside the nucleus do not contribute equally to the binding energy. Surface nucleons feels less force as compared to the inner nucleus. That we know that. So if you look at the nucleus, so from the center, binding energy will be more strong for binding force will be more strong at the inner part of the nucleus. The nucleons which are on the surface of the nucleus are not going to contribute much to the binding energy. Therefore, they feel less force compared with the inner nuclear part. Therefore, there is an energy difference or there is an energy turn due to the surface molecules or surface nucleons, that is ES, surface energy. It is always directly proportional to its surface rate, surface area. Surface area. So, if the surface area is more, therefore more number of nucleons will be present on the surface. Therefore, there will be a different energy difference will be there due to this outermost nucleons. Therefore, S is equal to S is directly proportional to the surface area. Therefore, S is directly proportional to 4 pi r square. Therefore, then if I rewrite that as S is directly proportional. How do I write this? 4 pi r square. So 4 pi r naught square into a to the power of 2 by 3. There, by replacing it proportionality constant, S is equal to S into e to the power of 2 by 3. So this also depends on its atomic mass number. Therefore, here S is defined as surface energy constant. Surface energy constant. So this is the second energy which is going to contribute for the binding energy. Then third one. Third one is Coulomb energy term. Why there is a Coulomb term? Coulomb energy term? Charge. Isn't it? Coulomb energy term is due to the protons inside the nucleus have Coulombian repulsive force. Right? So protons inside nucleus going to possess Coulombian attractive repulsive. This is Coulombian repulsive force, right? Why they are repulsive means same number, same charge, presence of same charge. Coulombian repulsive force. Due to this, there is a change in its energy. And therefore, Coulombian repulsive energy will be decrease binding energy of the nucleus. How the as the Coulombian repulsive force increases, its binding energy decreases, right? So this repulsive energy repulsive energy will decrease the binding energy of the nucleus. Binding energy of the nucleus. Therefore, this term is generally defined as like this. See, Coulombian energy, EC is equal to that is generally defined as 3 by 5 times 1 by 4 pi naught z into z minus 1 divided by r into e square. 3 by 5 ಅನ್ನೋದು ಎಲ್ಲಿಂದ ಬಂತು ಗೊತ್ತಾ? Do you know where we get this 3 by 5 term? Actually, this 3 by 5 on term ಎಲ್ಲಿಂದ ಬರುತ್ತೆ ಅಂದ್ರೆ quadruple movement of these protons. So generally we define that as a something 1 by 3 times ಏನೋ ಬರಿತೀವಿ, ಅಲ್ಲಿಂದ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡಿಕೊಂಡು ಬಂದಿದ್ದು ಅನ್ಸುತ್ತೆ ಇದು. ಇದಕ್ಕೆ ಕ್ಯಾಲ್ಕುಲೇಷನ್ ಪಾರ್ಟ್ ಏನು ಬೇಡ, ಜಸ್ಟ್ ಟರ್ಮ್ ಎನರ್ಜಿ ಟರ್ಮ್ಸ್ ಅಟ್ಟ ಬರ್ನು ಎಲ್ಲ ಕೂಡಿಸಿ ಬರೋದು ಬಿಡಕ್ಕೆ ಬರ್ತದೆ. Once if you look at this, if you look at this part, so this tells about the Coulombian force, electrostatic energy. This is electrostatic energy. Electrostatic energy, we can the 3 by 5 terms is going to define like energy, overall energy. So now statistical mechanics ಒಳಗೋದು. So we used to write that S divided by D plus S like this. So depending on the protons, depending on their dimension, so the total contribution of electrostatic energy is covered with the 3 by 5. Okay. This is equal to, we get that one as EC, Coulombian force or Coulombian energy due to the proton interaction, that is defined as 3 by 5 times 1 by 4 by epsilon naught, that is z into z minus 1 divided by, what is this r? R can be written as here. So we know that r equal to r naught into e to the power of 1 by 3. And I get this one as r naught into e to the power of 1 by 3. Therefore, if you look at all this, EC is equal to, consider this constant as, total constant as AC into z into z minus 1, divided by e to the power of 1 by 3. So here AC is the electrostatic Coulombian constant. We call this one as Coulomb energy constant. Coulomb energy constant. Coulomb energy constant. Next one is, so this is third energy. Yes. Fourth energy is defined as asymmetry energy term. Asymmetry energy term. What do you mean by this asymmetry? Nuclear for which Z is equal to N equal to Z are more stable. So departure from N equal to Z line results in the decrease in the stability. So the binding energy, its effect should be taken into account, isn't it? See, as if you take this N equal to Z, where stabilities these are more stable. More stable. If you deviate from, when it is deviation from N equal to Z, there binding energy decreases. So binding energy decreases due to decrease in stability. Therefore, the total binding energy is not same for all the nuclei. So generally, to define for all the elements, their stability is not uniform, or stability is not constant for all the elements. Therefore, that effect should be taken into account for the calculation of binding energy. Therefore, as if you go for this N minus Z, if it is N minus Z is 0, then we define it is more stable. If n minus z is non-zero ಇತ್ತು ಅಂತಂದ್ರೆ, so this actually measures the symmetry. Actually, this n minus z term, n minus z value defines about its stability or symmetry. This measures symmetry. So there is no equal number of protons or neutrons, as well as their stability also decreases. There, as the stability decreases, then binding energy also decreases. Therefore, we define this energy as asymmetric energy, asymmetry energy, that A is directly proportional to number of neutrons minus Z whole square divided by A. Because this n minus z is 0, then it will be more stable. There is no effect due to this part. If there is a deviation, then there will be this effect will be counted in case of total calculation of the binding energy. Therefore, A is directly proportional to n minus z whole square. Can I write this n minus z as a minus 2z? Because A is equal to z plus n. N is equal to A minus z. If I replace this n here, then what I get here? EA is directly proportional to A minus 2z whole square divided by A. So here, by removing this proportionality, I can rewrite that as EA is equal to some A constant into A minus 2z whole square divided by A. Okay, where this A is called as asymmetric energy constant. So this asymmetry is due to the variation of neutron number and proton number in the heavier nuclei. Then fifth, which is contributing to the binding energies, pairing energy term. Pairing energy term. Pairing energy term. So even nuclei, odd nuclei, we know that even is more stable, odd is least stable. Even odd and odd even are mediumly their stability will be medium. This effect should also be incorporated in the expression of energy, isn't it? So this even their part, even nuclei, odd nuclei, right? Even part of the proton and neutron, odd part of neutron and proton, even number of protons and odd number of neutrons, or odd number of protons and even number of neutrons. So that also affects the binding energy. So this is defined as this is pairing part. This is the pairing concept. Okay. So depending on their numbers also, stability varies. As stability varies automatically. So due to this, stability varies. Stability varies. Therefore, binding energy. Therefore, binding energy. Because of that, this part is also going to be considered into binding energy part. Therefore, this energy is defined as EP, pairing energy part, that is actually equal to plus times of AP divided by e to the power of 3 by 4. So this is for even. This is for even nuclei. So if there is odd nuclei, then we treat this as minus times EP, because if more stable, more binding energy. So therefore, even nuclei is going to be more stable. Therefore, it is contributing. It is going to contribute. It is not going to decrease. But in case of odd, so this is going to decrease its energy, binding energy. So we treat this as a minus AP e to the power of 3 by 4. 3 by 4. Hence, so binding energy, see, this binding energy is going to have all these 5 types of energies. So this will be
So
0.
that is 0
in
case of odd even.
Yes, correct. Between a point.
Odd and
0 in case of odd and even. So even and odd and even part, isn't it? So this will be treated as 0. So now total binding energy is going to be, so total binding energy is equal to, so one first part is, which is that first part? First part is a volume energy term. First term is volume energy term. So wait, I will write. So it is volume energy. Then next is surface energy. Surface energy. Then plus Coulombian energy term. Coulombian energy term. Next is plus asymmetric energy term. Asymmetric energy. Next plus another one is carrying energy. Carrying energy. See, tell me first. So binding energy, the total binding energy will be. So from volume energy, whether it is useful or means whether it is going to contribute positively or negatively. As the volume is more volume, if there is a volume is more, then its energy will be more because nucleons will be more binding energy will be there. Right? So this is going to help for the increase in the binding energy. Therefore, it is treated as AV into A because see here in the above case what we defined about the volume energy. The volume energy defined as AV into A, right? So it is going to contribute positively so to the total binding energy. The next, what about surface energy term? What about I told about the surface energy term? This surface energy term is going to decrease the binding energy or increase the binding energy? It actually it's a correction. It's a correction because we treat all the molecules, all the nucleons present in the nucleus are going to contribute for the binding. Means they are going to they will be bound to the uh, nucleon. Each there will be strong interaction will be there. But with respect to the central part nucleon, outermost that is surface nucleons are not going to have much uh, nuclear force, binding force compared to the central nucleon. So these are going to we need to subtract this part in the case of total binding energy. Therefore, it is given as minus times what is the term? AS. AS is a constant term. Okay. What is this? How it depends on atomic mass number here? Here is it a to a power 2 by 3.
A power 2 by 3.
So e to the power of 2 by 3. Then next, Coulombian force. Sir, is this Coulombian force is now to contribute or decrease the binding energy? Moreover, this Coulombian energy, if this force, if all these forces are attractive, then we could have considered that one as positively. But all these forces are repulsive forces, so that what is going to decrease the total binding energy that I have written here, I think, right? Repulsive energy will decrease the binding energy. Therefore, I need to take this one as negative. For minus sign, that is AC, z into z minus 1 divided by e to the power of 1 by 3. The next, asymmetric energy. This asymmetric energy is contributing positively or negatively? If there is a symmetry, if there is symmetry, then we could have taken this one as 0 because here n minus z is equal to 0. If that is symmetry, if the nucleus is symmetric nucleus, then we could have taken this one as 0. There is no contribution from this symmetric energy part. Symmetry tells about the negative part only. Therefore, it is going to be treated as minus times A. As it is going to deviate from a n equal to z line, then there will be asymmetry, there will be more instability. If there is more instability, there is a less binding energy. Therefore, it is defined as A minus times A minus 2z whole square divided by A. Now tell me parity. Parity energy, what should I take about parity energy? Sometimes it is going to contribute positively, sometimes it is negatively. Therefore, we need to take this one as plus or minus AP divided by e to the power of 3 by 4. Is it clear now, everyone? So this binding energy for the nucleon is calculated considering the different factors like its symmetry, its pairing, its surface part, and volume part, and Coulombian interaction between the protons and protons. Is this clear? Here these constants, I have written the constants, right? AV, AS. AV is the constant for volume energy, AS is for surface energy, AS is for Coulombian energy, AA for symmetric energy, and AP for parity energy. So these energies will be almost nearly equal to these parts. That is 1.14 mega electron volt, then this is 13 mega electron volt, and this will be 0.6 mega electron volt. These are the ranges of those constants. That is 19 mega electron volt, and that is 34 mega electron volt. So these are the constants for all those. What is the application of this semi-empirical mass formula? You know this? So what is the application of semi-empirical mass formula? Application of semi-empirical mass formula. The first application is to determine the binding energy of the nucleus. That is we know. The first one is to determine binding energy of any nucleus. Taking all the considered parts like pairing part, asymmetric part, and everything. Okay. And second one, determine the atomic masses of the nuclei. To determine atomic masses of the nuclei. Atomic mass of nuclei. Okay. Nuclei. And third one, study of energetics of alpha and beta decay. Study of energy of alpha and beta decay process. The fourth one, Q value of a fission process. Q value. Fission process. So it is the released energy. Fission process. Q value means Q is nothing but a released energy. Endothermic and exothermic process. Energy calculation part. And charge radii of mirror nuclei. Charge, then radii of mirror nucleus. Mirror nuclei. The sixth application is to determine the stable isobars. To determine the stable isobars. Stable isobars. Okay. Atomic masses in terms of semi-empirical mass formula. See, we know already this, right? What we had in case of binding energy. We had a formula that binding energy can be calculated by using the Z times of mass of the proton plus A in minus Z times of mass of the neutron minus mass of the nucleus and with Z array. This is the binding energy we knew. So here from this formula only you can calculate the mass of the nucleus. So if they have given the binding energy, you can calculate mass of the nucleus, right? Similarly, if you look at this, see, if I want to calculate the mass of the nucleus by using this mz is equal to Z times of mp plus A minus Z times of mn minus binding energy, isn't it? The binding energy, if you know the mass of the observed nucleus, then calculated part of the nucleus, the calculated mass and observed mass, you can calculate the binding energy. So you don't know what actually the observed nuclear mass. Then you can, if you know the binding energy, you can easily calculate mass of the nucleus. Because binding energy can be calculated by using the semi-empirical mass formula, by using its Z and mass numbers and everything we can calculate. Similarly, the same mass of the nucleus can be calculated just by substituting this binding energy here. So what we get, mass with Z mass, atomic number Z, mass number E, it is equal to, it's the mass of the nucleus. It's mass of any nucleus. Okay, so that is m is equal to Z times of mp plus a minus Z times of mn minus, what is the binding energy here? So the total binding energy defined as AV with A. So just remember, they may ask all these terms. So what is the dependency of energy on the atomic mass number? Whether it is proportional to A, whether it is proportional to e to the power 2 by 3. So like this they may ask. So AB into A, volume energy. Next, surface energy is defined as S into A to the power of 2 by 3. Then how it depends on Coulombian force? The minus times of AC into Z into Z minus 1 total by A to the power of 1 by 3. Next is asymmetric part. It is plus or minus. It is also minus. It is A into A minus 2 Z square divided by A. Then plus or minus AP divided by A to the power of 2 by 3 or 3 by 4. So it is 3 by 4. So this is what, by using the binding energy term, then its proton mass and neutron mass, we can calculate the mass of the nucleus. What if I want to calculate this? If it is the mass of the nucleus, okay, we can calculate by using this. What if we want to calculate the mass of the atom? How do we calculate the atomic mass from the same formula? How do we calculate the atomic mass? Here it is the nuclear mass, or mass of the nucleus. Then how do we calculate the mass of the atom using the same binding energy? Nothing, just replace this MP with MH plus MH. That's it. And
Yes, Mn.
by replacing mass of the proton with mass of the hydrogen, we can calculate the atomic mass. That is given by the same M with Z with A. So this will be atomic. But because we are going to add and subtract electron mass there. Done with this?
Sir, binding energy divided by C square and
So just ಬರೀತೀವಿ ಏನು ಕೊಟ್ಟಿರಲಿಲ್ಲ ಅಂತಂದ್ರೆ ಹಂಗ ತೋರಿ ಕೊಟ್ಟಿಲ್ಲ ಅಂತ ತೋರಿ
ನಡೀತೈತೇನ್ರಿ
ನೀವು ಮಾಸ್ ಬೇರೆ ಇದ್ರೆ ಇಲ್ಲಿ ಡಿವೈಡ್ ಬೈ ಸಿ ಸ್ಕ್ವೇರ್ ಆಲ್ಮೋಸ್ಟ್ ಆಲ್ ಕೇಸಸ್ ಒಳಗೆ ನಾವು ಏನು ಬೈಂಡಿಂಗ್ ಎನರ್ಜಿ ಹೆಂಗ್ ಡಿಫೈನ್ ಮಾಡ್ತೀವಿ ಸೊ ಮಾಸ್ ಹೆಂಗ್ ಡಿಫೈನ್ ಮಾಡ್ತೀವಿ ಮಾಸ್ ಎಲೆಕ್ಟ್ರಾನ್ ವೋಲ್ಟ್ ಡಿಫೈನ್ ಮಾಡ್ತೀವಿ ಆಕ್ಚುಲಿ ಏನು ಕೊಟ್ಟಿಲ್ಲ ಅಂದ್ರೆ ಏನಿರ್ತದ ಸಿ ಸ್ಕ್ವೇರ್ ಇರ್ತದೆ ಯಾವ್ದಕ್ಕಿದು ಮಾಸ್ಗೆ ಮಾಸ್ ಅನ್ನು ನಾವು ಯಾವಾಗಲೂ ಮೆಗಾ ಎಲೆಕ್ಟ್ರಾನ್ ವೋಲ್ಟ್ ಮೇಜರ್ ಮಾಡ್ತೀವಿ ಹೌದಿಲ್ಲ ನೆಕ್ಸ್ಟ್ ಕಾನ್ಸೆಪ್ಟ್ ಇದ್ರದ ಅಪ್ಲಿಕೇಶನ್ಸ್ ನೋಡ್ಕೊತ ಹೋಗೋದೈತಿ I told that we can from this we can calculate radius of the mirror nuclei calculate ಮಾಡಬಹುದು ಅಂತ ಹೇಳಿದೆ this is what the first property that we calculated we can calculate the mass number, atomic number and everything. Next is before going to liquid drop one problem ಆಗ್ತದೆ
liquid drop
ಪ್ರಾಬ್ಲಮ್ ಏನಿಲ್ಲ, ಸಿಂಪಲ್ ಅದು. ಮಿರರ್ ನ್ಯೂಕ್ಲಿಯರ್ ಬೇಸ್ ಮೇಲೆ ಮಾಡೋಣ. How do you calculate the mass difference between mirror nuclei? Mass difference between mirror nuclei. See that will see mass difference between mirror nuclei ನೋಡೋಣ್ರಿ. ನೋಡಿ ಬಿಡ್ತೀನಿ ಇಲ್ಲಿಗೆ. ನಾವು ಮಾರ್ನಿಂಗ್ ಕ್ಲಾಸ್ ಒಳಗೆ ಏನು ಮಾಡೋಣ, ಒಂದೊಂದಾಗಿ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡ್ಕೊತ ಹೋಗ್ಬೋದು. ನೆಕ್ಸ್ಟ್ ಇರೋದು ಏನಂದ್ರೆ ಕಾನ್ಸೆಪ್ಟ್ ಮಾಸ್ ಪ್ಯಾರಾಬೋಲಾ ಅಂಡ್ ಸ್ಟೇಬಲ್ ಐಸೋಬಾರ್ಸ್. ಪ್ಯಾರಾಬೋಲಾ ಗ್ರಾಫ್ ಬರ್ತೈತೆ ಒಂದು ಡೋ ಎಂ ಬೈ ಡೋ ಜೆಡ್. ಆಮೇಲೆ ಇದನ್ನ ಯಾವುದು ಈ ಸೆಮಿ ಎಂಪೆರಿಕಲ್ ಮಾಸ್ ಫಾರ್ಮುಲಾ ಯೂಸ್ ಮಾಡ್ಕೊಂಡು ಮೂಡ್ ಸ್ಟೇಬಲ್ ಎಲಿಮೆಂಟ್ ಅನ್ನು ಹೆಂಗೆ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡೋದು. By taking the differentiation of this semi-empirical mass formula, making it a zero, then if we calculate z there we get a most stable isobar. So most stable element, right? So that we are going to discuss in the next class. So before, let us see how to calculate mass difference in the mirror nuclei. So calculate ಮಾಡ್ತೀರಿ, what is the difference between mirror nuclei? What is the property of the mirror nuclei? Mass difference in mirror nuclei. So if you go for the mirror nuclei there, if I consider this x with z1 and with a1, y with z2 and a2. So what is the property of this? A1 will be always equal to a2, then a1 minus z2 is going to be plus or minus 1. Now if I take, see, if z1 is greater than z2, if z1 is greater than z2, then z1 minus z2 is going to be plus 1, right? So z1 minus z2 is going to be plus 1. Then for the mass, for the nuclei having the mass number z1, so atomic number z1, nuclei having z1 with a, I can rewrite this as z1 with mp, or z1 with mp plus a minus z1 times of mn, z1 times of mn, then minus times is AV part, volume part with A, then plus surface part with A power 2 by 3, then Coulombian part AC with Z1 into Z1 minus 1 divided by A to the power of 1 by 3, then plus then AA part with A minus 2Z divided by A to Z1. This is 2Z1 whole bracket square plus, so mainly minus plus
whole bracket square
plus minus ಬರಂಗಿಲ್ಲ, ಯಾಕೆ ಮೈನಸ್ ಒಳಗೆ ಮಲ್ಟಿಪ್ಲೈ ಮಾಡೀನಿ, ಅದಕ್ಕೆ ಮೈನಸ್ ತಗೋತೀನಿ, ಅಲ್ಲಿ ಪ್ಲಸ್ ತಗೋತೀನಿ. ಇಟ್ಸ್ ಎ ಇಂಟು AP ಏನ್ರಿ, AP divided by A to the power of 3 by 4. Similarly, if you took the same nuclear mass for Z2 with A, same ಹಿಂಗ ಬರೀರಿ, but then now you need to take the difference here, that is mass difference is given by delta M is equal to mass of the element Z1 with the A minus mass of the element with the Z2 A. Then here it is defined as delta M is equal to there is mass of the proton minus mass of the neutron plus 2 AC times divided by AC times Z1 minus 1 divided by A power 1 by 3. Because ಇಲ್ಲಿ ಏನು substitute ಮಾಡಿದ್ರೆ, we substitute that Z1 is equal to Z2 plus 1. So we have substitute everywhere, or Z2 is equal to Z1 minus 1. By substituting this in all the terms, there we are going to get only this AC part, because only Coulombian part ಅಷ್ಟೇ ನೋಡ್ರಿ, almost only Coulombian part ಅಷ್ಟೇ ಎದ್ರ ಮೇಲೆ ಡಿಪೆಂಡ್ ಅದ, Z1 and Z2 ಇಂಡಿವಿಜುವಲ್ ಮೇಲೆ ಡಿಪೆಂಡ್ ಐತಿ. ಅಂದ್ಬಿಟ್ರೆ ಏನು ಉಳಿದಿದ್ದು ಎಲ್ಲ ಕ್ಯಾನ್ಸಲ್ ಔಟ್ ಆಗ್ತದೆ. Z1 ಮತ್ತು Z2 ತಗೊಂಡ್ರೆ ಒಂದಕ್ಕೊಂದು ಕ್ಯಾನ್ಸಲ್ ಔಟ್ ಆಗ್ತವೆ. I left only with this part. So this is the mass difference of mirror nuclei. May I ask her? So this is ಅಲ್ಲಿ Z1 ಐತಿ ಕರೆ
ಸರ್ ಅಸಿಮೆಟ್ರಿ ಕೂಡ
Z2
ಒಂದು
minus 1 ಹಾಳೆ
Z1
ಸಬ್ಸ್ಟಿಟ್ಯೂಟ್
ಐತಿ
ಮಾಡಿದಾಗ ಈ ಟರ್ಮ್ ಕ್ಯಾನ್ಸಲ್ ಔಟ್ ಆಗುತ್ತಲ್ಲ. ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡ್ಬೇಕಿದ್ರೆ ಒಂದ್ಸತಿ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡಿ ಟ್ರೈ ಮಾಡು. This is the part. Okay. Direct ಕೇಳ್ತಾರೆ what is the mass defect of the mirror nuclei. This is defined as mass difference of defect ಅಲ್ಲ ಇದು mass difference. ಡಿಫೆಕ್ಟ್ ಅನ್ನ ಓನ್ಲಿ ಒಂದು ನ್ಯೂಕ್ಲಿಯಸ್ ಡಿಫೈನ್ ಮಾಡ್ತೀವಿ. ಇದ್ರೊಳಗೆ ಇದು ಥಿಯರಾಟಿಕಲ್ ಮತ್ತು ಅಬ್ಸರ್ವ್ಡ್ ಮಾಸ್ ಡಿಫರೆನ್ಸ್ ಅನ್ನೋದು ಬೇರೆ ಬೇರೆ ನ್ಯೂಕ್ಲಿಯಸ್ ಇದ್ದಾಗ. ದಿಸ್ ಇಸ್ ಡಿಫೈನ್ಡ್ ಆಸ್ ಮಾಸ್ ಡಿಫರೆನ್ಸ್ ಬಿಟ್ವೀನ್ ಮಿರರ್ ನ್ಯೂಕ್ಲಿಯಸ್. ಅಂಡ್ ಫ್ರಮ್ ದ ಸೇಮ್ ಅಬೋವ್ ಎಕ್ಸ್ಪ್ರೆಷನ್ ನೋಡ್ರಿ, ಮ್ಯಾಲಿನ ಅಬೋವ್ ಎಕ್ಸ್ಪ್ರೆಷನ್ ಅನ್ನೋದು ಯೂಸ್ ಮಾಡಿದ್ರೆ ಇದು ಟರ್ಮ್ ಏನಿದು ಟೋಟಲಿ ಏನ್ ಹೇಳ್ತದೆ ಹೇಳ್ರಿ ಇದು? It tells about the Coulombian force. So Coulombian force ಅನ್ನು ಹೇಳುತ್ತೆ ಇದು. Okay. From this expression we can calculate its radius and everything, because we know that Coulombian AC is equal to ಏನದ ನಿಮಗೆ? AC is equal to we know that 3/5 times 1/3/4 epsilon naught. Z1 Z2 ಕಾಮನ್ ತೆಗೆದಿರ್ತೀವಿ, ಉಳಿದಿರ್ತೈತಿ ನೋಡಿ ಸ್ಕ್ವೇರ್ R0 ಉಳಿದಿರ್ತೈತಿ. ಅದಕ್ಕೆ ಕಂಪೇರ್ ಮಾಡ್ಕೊಂಡು ಕ್ಯಾನ್ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಇಟ್ಸ್ ರೇಡಿಯಸ್ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡ್ಬೋದು, ಇನ್ನುಳಿದೆಲ್ಲನೂ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡ್ಬೋದು. ಓಕೆ. ಸೊ ನಾ ಮಾರ್ನಿಂಗ್ ಬಂದ ಇದ ಕಾನ್ಸೆಪ್ಟ್ ಮಾಸ್ ಡಿಫರೆನ್ಸ್ ಅನ್ನ ಇಟ್ಕೊಂಡ ರೇಡಿಯಸ್ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಹೆಂಗ್ ಮಾಡ್ತೀವಿ, ಅದಕ್ಕೆ ಚಾರ್ಜ್ ಹೆಂಗ್ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡ್ತೀವಿ ನೋಡೋಣ. ಅದ್ರ ನಂತರ ವಿಲ್ ಗೋ ಟು ದ ದಿಸ್ ಮಾಸ್ ಪ್ಯಾರಾಬೋಲಾ ಅಂಡ್ ಸ್ಟೇಬಲ್ ಐಸೋಬಾರ್ಸ್. ಮಾಸ್ ಪ್ಯಾರಾಬೋಲಾ, ಸ್ಟೇಬಲ್ ಐಸೋಬಾರ್ಸ್. ಎಸ್, ಎರಡು ಪ್ಯಾರಾಬೋಲಾ ಗ್ರಾಫ್ ಬರ್ತಾವ್ರಿ, ಸ್ಟೆಬಿಲಿಟಿ ಅನ್ನು ಡಿಫೈನ್ ಮಾಡ್ಬೇಕು. ಆಡ್ ಅಂಡ್ ಇವನ್ ಜೆಡ್, ಇವನ್ ಎನ್, ಆಡ್ ನಂಬರ್ಸ್, ಇವನ್ ನಂಬರ್ಸ್, ಏನೋ ಕಾನ್ಸೆಪ್ಟ್ ಐತ್ರಿ. ಐ ವಿಲ್ ಡಿಸ್ಕಸ್ ಇನ್ ದ ನೆಕ್ಸ್ಟ್ ಕ್ಲಾಸ್. ಶಾರ್ಟ್ ನೋಟ್ಸ್ ಕಳ್ಸಿನಿ ಇದ್ರದ.